Okay, so the next doubt posted in the group is this: a horizontal tube of length L closed at both ends contains an ideal gas. So you have a tube of length L, let's say this is L, it's closed at both ends, okay, like this, contains a gas of molecular mass M. It's molecular mass, not the total mass. The tube is rotated with angular velocity omega about a vertical axis passing through one end. Okay, so let's say this is one end, a vertical axis. 1 second. So this is about one end, vertical axis. It's rotated about a constant angular velocity omega. If the temperature is constant and P1 and P2 are the pressures at free end and fixed end. Free end means the one that is free to rotate. So this is P1, pressure P1 or pressure free end, and fixed end. Fixed is this. So P2. So this is P1, this is P2. Then they just want you to find the relationship. You can do it just by looking. You see, when you rotate, what happens is this is just like normal rotation. Okay, so let's assume that you are inside this chamber. Okay, you are standing here, and the chamber is getting rotated with this angular velocity like this. So what will happen? You will feel a force backward, right? So as this rotates here, you will be feeling a force, because in your non-inertial frame, you will feel a pseudo force that is acting outward. So you'll be pushed out. So same thing will happen for the gas molecule. So what will happen is, initially, before you rotate, the gas molecules will be evenly distributed. Everywhere pressure will be same. Initially, if you don't rotate, P1 will be equal to P2. As I rotate, the gas molecules feel a force outward. So they start piling up here. So there will be more number of gas molecules here. So the pressure here will be more compared to the pressure here. So P1 will be greater than P2, simply because the gas molecules are getting pushed out because of the centrifugal force. Okay, so P1 will be greater than P2. This is straightforward. Okay, but if you want to calculate it, you don't need to do it for neat point of view, but if you want to calculate, the idea is very simple. Just show it, but technically the problem is over. If you want to calculate, the idea is very simple. So what we'll do is, since the pressure is changing continuously from here to here, we cannot do it in one stretch. I have to consider a small portion. You can consider it anywhere. Let's say I take a small portion, thin portion. I'll find the pressure. So here at this end, the pressure is P, and at this end, it is P plus dP. You understand? Pressure increases as I go from here to there, because there are more molecules there, it gets pushed away. Okay, so your pressure is more. So here, if the pressure is P, after a small distance, the pressure is P plus dP. Okay, so what you need to understand is the pressure is perpendicular to the surface always. So this pressure is acting this side, P, this pressure is acting P plus dP this side. So that's a net pressure acting towards the what is that, left. Okay, so on this element there is a net pressure. Okay, so P net is P plus dP minus P, which is just dP. That's a net pressure acting, and I can convert this into area. Therefore the net force acting on that element is P net into the area. Area means this is the area we are considering, this area, cross section area. So this is A into dP. I hope you understand. And what does this pressure help, net force helps us to do? Remember this portion, this green color portion, as the tube rotates. Maybe I'll try it. This is the tube. The tube is going in a circular path. And this green color portion is also going in circular path. And anything that goes in a circular motion should be acted upon by a force equal to the centripetal force. And this force is the only thing that is providing the necessary centripetal force. There is nothing else in contact. So this pressure difference along across this thin layer provides the necessary centripetal force. So we can say that this F net must be equal to mv square by r. And what is r? I mean, this radius. So let's say this is at some distance x. Okay, and this thickness is dx. So the radius here will be x. I hope this is clear. And I can write this in terms, I don't want to write mv square by r. I'll write the centripetal force is mr omega square, because they have given me omega. So it is mr omega square, m, mass of this layer of gas, thickness, r is x, omega square, mr omega square. Okay, this F net is AdP. A into dP is the net force acting on this. Okay, and this is the mass, x into omega square, that's constant. How do you find the mass? Mass is volume into density. Okay, so this is volume. Don't say it's a full volume, it's only the volume of this layer. I'll come for it. Volume into density x omega square. How do you write the volume? Volume is area into length, thickness, dx. So the volume is area, thickness is only dx. I'm only writing this mass is the mass of this green portion of gas. Understand that. So A dx rho x omega square. Now, how do you find rho? We go for the PV equal to nRT. We have done this many times. P equal to nRT. N is total mass by molar mass. Total mass by molar mass RT PV. Now, what you can do is here, I need density, mass by volume, total mass by total volume. So this will be PM by RT is equal to density. Is it okay? So this is the density of the gas at this portion. I'm going to assume the density is almost constant for this full layer. It's a very thin layer, so you don't have to worry about the changing density. So density at this end, which is the P pressure at that point into M by RT, is the same almost uniformly everywhere. It's very thin. That's the whole point. So for density rho, so I can write A dP is equal to A dx. The density part, rho part, the rho is Pm by RT, the pressure at this end, molar mass, okay, by RT into x omega square. So we lose the A. I can collect the terms, okay, pressure terms on one side. So it is dP by P, mRT, omega, constants, you get it one side, m omega square by RT, x dx. Now, obviously, I have the variables, I have to integrate to find the variation of pressure along this. Okay, so this integration starts from P2 to P1. Okay, this is from P2 to P1. When x changes from, x is the distance, radius, right? So when I'm P2, the x is 0. When I'm at P1, the x is the length of the tube. When I'm at P1, the x, this radius should be equal to length. This is from 0 to L. It's a normal integration. This will give me ln P and upper limit minus, I don't have space, so I hope you understand. Upper limit minus lower limit. This is equal to m omega square by RT L square by 2. That's all. So if I simplify this, I'll get, I mean, you can take the exponential on both sides, ln e power. So P1, the pressure at this end, P1 is equal to P2 into exponential of e power m omega RT by 2. Okay. So m omega square L square by 2 RT. So see whether you understand this. So this is how, sorry. Yeah. So this is how the pressure changes exponentially. Okay, and as you can see, P1 is greater because it's e power plus. You can write it as some constant. So P1 is equal to P2 e power some KL. Okay, so the P1 is greater than P2 exponential times. Okay, but we already seen that P1 is greater than P2 is the answer. If you want the exact value, this is the full derivation. Okay, so those who want clarity, you can watch this, see whether you have understood all the arguments, logics. If you have any doubts, ask me in the Telegram channel. Okay, link in the description. For new students, if you like the video, hit the like button, and you have the Telegram channel link. Join the Telegram channel to post your doubts and get video solutions. The complete 11th and 12th playlist is there in this YouTube channel. You can watch to get your doubts clarified. Okay, so keep practicing. All the best.